Today's topic is going to be probability of independent events. There's going to be a little activity that you do in class to help solidify what the difference between independent and dependent events are, but here's some vocabulary to start with. Two events are independent if the occurrence of one event has no effect on the likelihood of the other, and if one event does not affect the others, that would be dependent. So does not affect independent, does affect dependent. Our first example would be, what if we have Michelle and Daryl, they each have some spare change in their pocket, and we want to find the probability of getting a dime from Michelle and a penny from Daryl. What's the probability of getting a dime-penny combination? So first choice would be, if we would write this like we did the others, it would look like, what's the probability of getting a dime and a penny? And so that probability, we would say, is take the probability of getting just the dime and times it by the probability of getting just the penny. And that should be our result. So let's look at Michelle. She had 4 dimes, 6 quarters, so we have a chance of 4 out of 10 coins being a dime. And for Daryl, we have 5 pennies out of 8. And again, do the math. We should be canceling here to help. 4 goes into 4 once, 4 goes into 8 twice. 5 goes into 5 once, 5 goes into 10 twice. Straight across the top, we get a 1. Across the bottom, we get a 4. If you like percents better, then 1/4 would turn into 25% of getting a dime-penny combination. Now, the next example gets a little more complicated process. In a class of 20 students, what is the probability that 2 or more of the students have the same birthday? All right, and we know birthdays can happen any day of the year, so we start thinking, well, 2 or more of the students have the same birthday. What if we said none of them has the same? None of them has the same is basically the probability of all different birthdays. And when we start thinking of that every single day, and so we'll think of it as our first person would be 36/5, so to 365 days. They could have their birthday any day, and then the next person could only have it 364 days out of 365, so that we have no repetition. 363 out of 365, right on down to 346, because remember, we only have 20 students in our class. 365 take away 20 is 345, so the 346th would be that 20th term. Looks like it's about 59%. With that, we want you to say, well, wait a minute, in this scenario, what if 2 or more were the same? We could think of it using our complement idea. 2 or more being the same birthday would be the same as 1 minus all different. That's our samplement. Our complement sample space is 1, and then all being different. So if we look at this, we already have the math done. 1 minus that decimal, and we subtract, and we get that 41, and that 41% should be what we need to finish, in this case, of what is the chance of every student in that class of 20 having different birthdays. 2 or more the same is 41. All different, 59. So we use a complement idea to get our solution here. These are the formulas now that we have had, and we want to make sure you're clear on them. Mutually exclusive, you would add the different probabilities together. Inclusive, probability of A or B happening, we have to subtract the overlap. Complement, we just used on that last example, and then the independent events, P and B happening. So with these 4, you're going to be solving most of your probability problems that we've done so far. Okay, if you have any questions, bring those to class and we'll discuss it.